Yeah, hi all. So last time we discussed this, the simplified AdWords problem reads like the following: that uh, assume all bids by the advertisers are 0 or 1, and each advertiser has the same budget, and per query only one advertiser has to be chosen. Okay, so this was a simplified model, and we tried the greedy algorithm on the simplified model, and let's say with two advertisers A and B, and where A bids only on query X, B bids on both queries X and Y, and if both have budget 4, with this kind of a query stream with 4 X's and then 4 Y's after that, the one of the possible runs of greedy algorithm would have produced this allocation, and then all X's would have gone to B and nothing would have gone to A, and the Y's couldn't go to A. So the optimal allocation could actually exhaust the full revenue 4 plus 4 8, whereas the greedy allocation would have only exhausted revenue 4. So the competitive ratio would have been at best half, right? So this was actually the worst case. Okay, now then we discussed quickly that for the simple case, another algorithm called balance will actually do better. What it will do is, for each query, pick the advertiser with the largest unspent budget who bid on this query. So the idea about behind this is keep spending everybody's money so that it doesn't happen. I mean, you give everything to one advertiser and then that guy's budget is finished, but when other queries come which could have been given to this advertiser, you have nothing left, right? So so in the same scenario, this kind of a query stream, balance would have allocated something like this: BA, BA, BB. Last two would have been left empty. However, the optimal would have been this. So the competitive ratio would have been at best 3 by 4. That means in this particular instance, it would have obtained competitive ratio 3 by 4. So we know that the competitive ratio cannot be better than 3 by 4. So competitive ratio is at best 3 by 4, but it did better than the greedy thing. Okay, so this is where we ended last time. All right, and now we will start today by analyzing the balance algorithm and trying to see whether is it just this input for which it would achieve this competitive ratio 3 by 4, or for any input in the simplified case, it will actually achieve that. So consider the simple case of two advertisers only, and each with same budget. Let's say B, some budget B, which is an even number, just to make sure that it's even number, because you have two advertisers and it will actually be easier to calculate that way. So consider the case where the optimal solution exhausts both advertisers' budget. So assume that in the optimal case, if you could do a magic, you would have finished all the money of both the advertisers. Then the optimal revenue to the search engine would have been 2 times the budget, right? So each would have had 2B. Now in that case, the first claim is that balance must exhaust at least one advertiser's budget. So what happens if both advertisers have something left? For it, so we could allocate more queries, right? So the reason why balance was stuck must have been because at least one of the advertisers budget was finished. Now without loss of generality, let's assume the balance of A2 was finished. So in the budget of A2 was finished by the balance algorithm. Okay, so just reiterating this part again, we are analyzing a scenario where the bids are 0 or 1, two advertisers, both with same budget, and the optimal case, for some query stream, the optimal case would have finished all the budget of both the advertisers. However, the balance algorithm has only been able to finish one of the advertiser's budget. Okay, and then it was stuck because the further queries could have been allocated to that advertiser, but that guy doesn't have any more budget left, right? So that's the scenario where the balance will not be optimal. So now let's see how bad can the balance algorithm be in this such a case. So suppose um, these are your queries. Okay, so of course it's like a bar, but suppose it speaks volume, so more like these many queries. Okay, so the blue queries are the queries which are allocated to A1 in the optimal solution, and the green ones are allocated to A2 in the optimal solution. So suppose there is an optimal solution like this, where the budget is of course this much. Each bid is 1 or 0, right? So 0 means no bid, 1 means exactly 1. So these many queries were allocated to A2 in the optimal solution means each query would take budget 1. So this much is the budget, right? So this is the B budget. And since the balance algorithm did not reach the optimal, it must have been this way, that we assumed the advertiser 2's budget would have remained unspent, oh sorry, exhausted. Advertiser A2's budget would have been exhausted. So what must have happened is A2's budget was filled up, but A1's budget remained empty for some. Okay. So what has happened is optimal revenue was 2B, and the balance revenue must have been something like 2B minus X, where A1 had X budget left. And this much budget left from the picture, it is clear that this much. Okay, so basically we'll talk about it just a moment later. And then the claim is the this white part that is left must be only green queries. What are green queries and what are blue queries? The green queries are the ones which would have been allocated to A2 in optimal, and blue queries are ones which would have been allocated to A1 in optimal allocation. Now, in the balance allocation, obviously the allocation would be different, right? It doesn't have to, all blue may not go to A1 or all green may not go to A2. Now the question is, since uh, this has happened that your green part is remaining, okay, the remaining this much budget must have been remaining, and these many queries must be only the green part. Why? Because if I had some queries not allocated and if there was some blue in that, I could then further allocate it to A, because A definitely takes all blue queries, right? So A definitely takes all blue queries. So if there was any blue here, I could allocate to A, then X would have been smaller, right? So whatever X was unspent in A's budget, it must correspond to this green part. Okay. So then the next claim is this Y, this blue plus this green part must be greater than or equal to X. Okay. Why? If we can, first of all, if we can prove that, if we can prove that Y is greater than or equal to X, then we have the result, because then the balances allocation would have been this whole part plus half of it. So, you know, 3/4 of whatever the full allocation could have been. So then balance minimum revenue. Okay. Um, so balances revenue will be minimum when X is equal to Y, and that is B by 2 in this part, and this is full B. So the minimum balance revenue would have been 3B by 2. Here I should really write balance revenue is minimum for X equal to Y equal to B by 2, and this full thing actually would have gone to A1. A2 has got A2 has given revenue B, right? So B revenue from here and B by 2 at least from here. If we can show that Y is greater than or equal to X, then our claim is proved that our balance algorithm has produced revenue 3B by 2. And the full revenue optimal is 2B. So if we can show that balance produces revenue minimum 3B by 2, then we know that the competitive ratio for balance is 3 by 4. Okay. So that means we need to show that this part, the budget spent for A1 has to be at least the budget unspent for A1. So let's try to do that. Case 1, so we'll take two cases. Case 1 is at least half of the blue queries are assigned to A1 by balance. So the blue queries are here. Blue queries are the queries which in the optimal solution were assigned to A1. Which of those are assigned to A1 in balance? Okay. So the first case is at least half of them are assigned to A1 in balance. Well, in that case, it is clear because if we have half of this is B. So if half of them are assigned to A1 already, then Y is already half of it, right? So then we are done. So then Y is at least greater than equal to B by 2. Right? So blue alone, the blue queries are alone B, right? So this case 1 is this one. However, if half, lesser than half of the blue queries are assigned to A1 by balance, then what? Then let Q be the last blue query assigned by balance to the other advertiser, A2. So blue and green queries have come in the stream, and let Q be the last blue query assigned by balance to A2. Now A1 also bid on a Q because Q is one of the blue queries, right? So A1 also must have bid on Q at that time, and the budget of A2 must have been at least as great as that of A1. So balance works in the following way. When the query Q came, check which advertisers are bidding on it, and then give it to the advertiser who has the most unspent budget left, most money left. Now, if there is a tie, then you can give it to any. So since that last query went to this guy, and we know that both of them bid for it because in the optimal solution, that blue query would have been given to A1. So then, but in the balance, it was given to A2. That means the budget of A2 at that point of time must have been at least as much as that of A1. Now, since more than half of the blue queries are assigned to A2, so we already, this is the case 2 where we are saying that no, not half of the blue queries are assigned to A1. So since more than half of the blue queries are assigned to A2, at that time A2's remaining budget was less than half of it, because half of blue queries will actually exhaust half of your budget. So since more than half of blue queries were assigned to A2, at that time half of its budget must have been finished. Now since A2's budget was more than half finished, A1's budget also must have been more than half finished, because otherwise it would have been given to A1, right? So then the budget of A1 also was at least half finished. So this means X is less than equal to B2, and therefore what we have is the unspent amount is less than half of the budget. Okay. So then again, it proves that the balance uses at least 3B by 2 of the total budget by the two advertisers. Okay. So is this proof clear?
Yes, sir.
Okay. Everybody else, I just want to verify that everybody understood the argument. It might sound a bit complicated at the beginning. All right. So if so, then let's move forward. So now, so what did we show? We showed that balance obtains or achieves a pretty good 3 by 4 competitive ratio in the very simple case. But now we'll slowly make more realistic assumptions instead of the very simplistic assumption. So many bidders. So many bidders, if from two bidders we have, first of all, many bidders, but we keep the other condition the same. Other condition is everybody still has the same budget. So then what happens? So let's look at one example of that. So let's say we have n advertisers, everybody has budget B, and we have n distinct queries, Q1 to Qn. Now in the query stream, of course, we have n distinct queries. That means some of the queries will repeat. So how is the query stream coming? The ith round will get only query I b times. So it's more like first round only Q1 b times, second round only Q2 b times, third round only Q3 b times, and so on. Ith round. So instead of looking at one query at a time, we will now look at, let's say, I queries at a time in a batch or something like that. So ith round, same query Qi repeated b times. So that means total n times b queries will appear in n rounds. Now, let's first look at the advertiser's bid scenario. So let's assume, so we are actually constructing an example, a bad example for which balance or some other algorithms will actually do bad, right? Will not do so well. So this example is like the following: that advertiser AI bids only on Q1, Q2, Qi, not on the other queries. So there are queries are from Q1 to Qn, n different queries, but advertiser AI bids only on Q1 to Qi. That means A1 bids only on Q1, A2 bids only on Q1 and Q2, and so on. Now, what happens in round one? Round one, you get B queries, all of them are Q1. Okay. So then, who are the possible allocate? I mean, whom can you allocate that query? Okay, round one, you can allocate it to everybody because everybody bids on query one. Everybody bids on query one. Okay. So you can allocate it to all, I mean, any advertiser you want to AN. What about round two? Round two, uh, so just a moment.
Yes, sir, it's all right.
Yeah, this is all right. Yeah. So round two, our queries are Q2, 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 right? So round two, our queries are only Q2 B times. Now A1 bids only on Q1. So A1 cannot be allocated that those queries. So that means only A2, A3, AN can be allocated the round two queries. Similarly, for round I, up to I minus one advertisers are not going to bid on query I. So AI onwards advertisers can be allocated the round I queries. And similarly for round N, only the last advertiser can be allocated. Now, suppose you knew this query stream in advance, which is not the online case, right? So basically the magic we talk about is the offline algorithm, right? So if you wanted to do this in the offline case, then what would be your optimal allocation? Well, you will allocate all queries in round I to AI. So because you know that after first round, A1 cannot be given anything. So you spend A1's budget, all budget B by the B queries in the first round. Okay. So that is if you know your query stream is going to be like this. Okay. If you knew in advance everything, then what will you do? First round totally goes to A1, second round goes to A2, third round goes to A3, and so on. And the nth round, you have to give everything to AN anyway. And then you will, of course, you will exhaust all budget. So the optimal revenue is going to be NB. All right. So this is fine. Now, what if you apply the balance algorithm on this? Then balance algorithm cannot allocate allocate all B queries to one and spend all that guy's budget, because that's not how balance works. So balance works by kind of maintaining everybody's remaining budget the same, right? So it basically tries to do that. So how does balance work? So suppose these are your advertisers. Balance algorithm on this example. And what will happen after k rounds? We'll come back to that in a moment. Let's first look at the picture. So first round, what will balance do? Total B queries, there are n advertisers. So it will kind of balance it out to everybody, because the first round query, everybody can be allocated. The second round, A1 cannot be allocated. So B by n minus 1 to everybody. right? So n minus 1 advertisers remaining, b by n minus 1 to everybody, and the third round b by n minus 2 to everybody, and so on. Now look at this. If it was b by n for all n rounds, everybody would have exactly finished their budget B. But the allocations are actually increasing. B by n minus 1 is slightly larger, B by n minus 2 is slightly further larger, and it will be larger and so on. So we will not actually go for n rounds. So the queries will come for n rounds, but even before that, these some people's budgets, basically all the people's who are eligible here, so these people will not even participate because they don't even bid on the later queries. Basically these people's budget would get finished. So essentially what will happen after k rounds, what is the sum of allocation to ak to an? Ak to an means these are the ones who can still take it. So that if we call it the sum is sk plus 1 and so on Sn, that's actually going to be the same, because after the first round everybody would have been allocated the same. After the second round, a2 to an would have been allocated the same. So essentially after kth round, sk to Sn would have been the same, and that is sum of I equal to 1 to k b by n minus I plus 1. Essentially this sum, right? This sum up to k such terms. And that is, if you can take the b out because b is a constant here, b times this quantity. Now, as I just mentioned to you that these portions are actually increasing, so we will not actually be able to run it for n rounds, right? We will stop somewhere before, and we'll get stuck somewhere before. So if we find the smallest k such that this quantity is already more than b, my budget is exhausted, then after k rounds, we cannot allocate any queries to any advertiser. So our goal here is to figure out when do we get stuck. We are analyzing the balance algorithm on this particular example. The goal is to figure out when do we get stuck. So this algorithm cannot allocate any queries after k rounds if b times this thing is greater than equal to b. That means this whole allocation exhausts the budget b. In other words, this, I mean, you take the b's out from here, right? So b is a constant, positive constant. In other words, this sum 1 by n minus I plus 1 I equal to 1 to k, if you just write it out, you will see that is 1 by n plus 1 by n minus 1 plus dot 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 1 by n minus k plus 1. Okay, so this you want to be greater than equal to 1. You want means you want to find out when we get stuck. So when this happens, we get stuck. All right. Okay. So this is the sum. This quantity, as soon as it becomes greater than equal to 1, balance cannot allocate any more queries. When does this happen? This happens, to do this, we will actually use this limit. Okay. So this limit is 1 plus half plus dot 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 1 by n. It converges to log n to the base e for large n. So rather limit of this sum is log e to be log n to the base e for n goes to infinity. Now, is our n large? Well, n rounds. That means eventually what happens, right? So lots of queries are coming. Yeah, in real case, n is kind of large. Okay, so we want to find a k so that our sum 1 by n plus 1 by n minus 1, this is greater than equal to 1, and we'll use this to approximate this part. Yes, how should we do? Note that this sum is, if you do the sum from 1 by n to 1, actually written reverse. Okay, so 1 plus half dot 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 1 by n. So I just write it reverse, 1 plus half plus 1 by n, and you subtract 1 plus half plus 1 by n minus k, right? So the terms which are remaining are basically this sum minus this sum, right? So what you actually want is this sum minus this sum is greater than equal to 1. Just verify that these are the terms which are not in here but in here. Now these can be approximated by log n, right? So this means what we want is this is log n minus k, okay, and that is log n by n minus k, and we need that to be greater than equal to 1. And that you can just work it out that it's n minus k by n must be less than equal to 1 by e, or k has to be greater than equal to n times 1 minus 1 by e. Okay, so this means as soon as you run it for k rounds, which is n times 1 minus 1 by e, okay, n times 1 minus 1 by e rounds, balance algorithm cannot proceed any further. So up to that, it was exhausting B budget per round. It was allocating all queries until that moment. And after that moment, it cannot allocate any query. That means what would be the revenue? The revenue will be in every round, it was actually spending budget B of some advertisers altogether. But after that, it will not be able to do anything. So B times N times this. That means our optimal budget allocation would have been Bn, but it is one Bn times this factor. So the competitive ratio is actually 1 minus 1 by E, which is kind of 0.63. So what changed? Our simple case was two advertisers, everybody had same budget. This case is more than two advertisers, still everybody has same budget. Okay, and we see that the competitive ratio is at best, because we have produced an example where the ratio is 0.63. So the competitive ratio is at best 1 minus 1 by E, which is around 0.63. Now let's take a pinch of salt here and let's try to understand what this means. So what did we do? We created a very pathological example and made the balance algorithm work really bad. Really bad means, the competitive ratio came out to be 0.63. So this is actually a theoretical measure, right? It's a lower bound kind of a thing. Actually, let me tell you these two couple of things first. So this paper, there are basically two papers which are very important. We will not actually do the proofs, but the two papers, one is in theoretical computer science, another is in Fox in 2005. So this paper, basically they proved that the competitive ratio of balance in this particular scenario is indeed 1 minus 1 by E. That means, well, this is actually the worst case example. So this is the worst case example. So we know that the competitive ratio is at best this, but they also proved that it is this. And the other very interesting result is no deterministic online algorithm can have a better competitive ratio. That means whatever you design another deterministic online algorithm, okay, you um, you can have some example which will produce which will make your competitive ratio as bad as 1 minus 1 by E. Okay, so these are the two results. Now what does this mean really? This means that balance algorithm can produce a competitive ratio which will kind of waste chances of making the rest 37% of the money, but that is only the worst case scenario. In many cases it will actually do better. Okay, so that is basically what this means. Let me pause for a moment here and let me ask you whether you have any question on this proof that we just completed, the worst case scenario proof.
Sir, every query, like query I is having n instances
B,
at every round.
B.
Okay, B.
Yeah. Okay. This is the setting. Oh, sorry. Ith round, query I repeated B times.
Okay, okay.
So total n times B query, n rounds. Okay. Every round B query. So essentially the idea is every round you. So if everybody would have bid for every query, then you would have simply allocated B by n to everybody in every round, and this would have gone on, and you would have finished everybody in a very uniform way. Essentially, basically, this takes one, is this just the sum actually, 1 by, yeah, 1 plus, sorry, 1 by n plus 1 by n minus 1 plus 1 by n minus 2 and so on. So that's basically the idea.
Sir, every round they will have the same budget B.
Everybody has the same budget B.
Every round budget does not decrease.
Of course, budget decreases, right? Every round the budgets decrease.
So how does B by n, and in the next round it becomes B by n minus 1? It should be less than B in the numerator.
No, 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 no. Okay, so the way balance works, let me actually, okay, this picture is fine. So way balance works is, first look at which are the advertisers who are bidding for this query, then allocate it to the one who has the largest budget remaining. Now, initially everybody has budget B. The colored portion is the finished budget and the white portion is the remaining budget. Second round, this is not the budget, okay? This is the budget I have allocated. Basically, this is the budget spent in this round. So the first round is the blue round. Okay, everybody's B by N budget is gone. Next round, everybody's B by N minus 1 budget is gone, but remaining is only this much. So remaining is 1, or remaining is B minus B by N minus B by N minus 1. Okay, but that's not really the problem here, because after the first round, everybody still has the same budget remaining. Only A1 does not bid on query 2. So query 2, only these are the people who are bidding on query 2. And you allocate them equally, right? Just to keep their budgets similar. So now, for example, what could be B by N minus 1? Right, so you have B queries. Suppose B is like something like 100. Okay, so B is like 100 and N is like 20 or something like that, or B is like a 1000, N is 200 or
Sir,
something.
n is the number of queries.
N is the number of rounds.
Rounds.
Yeah, and B is the budget. Now, so basically these are all fractions, whereas our initial assumption was that it's either 1 or 0 kind of thing. But when things are large enough, I mean, you can make them similar to integers. So the analysis here is not assuming that they are fractions. You can always make them granular. Yes?
Sir, in the second round, when we have B instances of Q2,
right,
then we'll give one each to A2 to N. Then we can give another one to any of the others, right?
No, we have B instances. So here you should think that B is much larger than N. So think of it that way.
Okay. Then we will always give everybody equivalent.
Yeah, it's like equal means it can happen that, of course, ultimately it's quantum. So it can happen that, A2, A3 gets slightly more than the rest, but in the next round you will compensate on that, right? So
yes.
So essentially, yeah, when you analyze, it makes sense to analyze it this way. I mean, not all of them will be always integers, but it makes them to analyze just.
Yes, sir. Okay. Next round it will balance out. So.
Yeah, next round will balance out. So only for very small B and N, of course, it will look like, you have to give one more here and then you cannot give anything. But in the next round, it will balance out. When things are large enough, then you will more or less be similar. So yeah, it may be slightly large here or somewhere, and the next round it will kind of. So more or less approximately it's like this. And third round, only this. The main idea is this, that every round, the amount of allocation increases because the denominator decreases. And then you cannot actually go on for n rounds. So that is basically the whole idea.
Okay.
All right. So so that's basically this part. All right. Please go through it again later on. Now let's talk about slightly more general case. We'll not really prove any further result here in this, but we'll know that what happens. So general case is when our assumption still was that everybody had the same budget, but that's again realistic. Different bidders So suppose a bidder A1 and A2 both bid on all queries, let's say, but basically, yeah, can you hear me? Okay, I
Yes,
just had,
yes, sir.
okay,
Yes, sir.
fine.
We can
Okay,
hear.
my internet connection said unstable for a second. Okay, so suppose bidding is not a problem. They both bid on queries, but the bids are for A1, the bids are 1 unit or $1, but the budget is a lot. And for A2, it's $10, but the budget is small. Now, what would balance do? Balance will focus on unspent budget, right? So suppose your query stream is this query comes 10 times. Okay, so what will happen? Balance will look at every time, it will look at A1's budget is still more. So it will give it to A1, then it will become 109 and so on. So it will still come to 100. So all 10 queries will go to A1. So the revenue earned will be 10 because every time you give it to this, the revenue is 1. However, if you want to maximize your revenue, okay, then you can actually allocate all 10 queries to A2 and exhaust A2's budget, and you can actually earn 100. So this means the competitive ratio for this particular example, I mean, I'm using the word competitive ratio in a loose instance based case here. You understand what we mean. It's 1 by 10. Now you can actually construct more examples, curated examples to make the competitive ratio much smaller. I mean, you can do this, for example. I mean, um, oh no, so I'm sorry. Yes, this will probably not be a good idea. Just a moment. I closed it. Yeah, so something like just a moment. Yeah, something like this maybe would be fine, right? So A2 bids 20 with budget 200. A2 A1 bids 1 with budget 210 or anything. You make the budget anything large. Okay, doesn't matter. So you can actually make up numbers here, and then the competitive ratio will be 1 by 20 here. Right. So you can actually make it as small as possible. Hence, the worst case scenario will converge to competitive ratio equal to 0. Right. So you can make number of queries large, and you can take this to any kind of limiting scenario. So this means that when different advertisers have different budget, mm, then balance as is not that good, but it can be actually modified. Okay, so the generalized budget balance algorithm works in the following way. So there are two things to be done. One is be biased in favor of higher bids, and two is consider the fraction of remaining budget and not the absolute remaining budget. So if somebody started with large budget, you finish that guy's budget also, but it's just a fraction of the budget. So basically, you have to take care of both these parameters. I want to make a point here, which I did not re-mention in the slides here, that remember that in the actual AdWords, one of the main innovations was not pay per impression, but pay per click. So all the time we are talking about allocate query to A1 or A2. So let's say I allocate all 10 queries to A2. What do you mean by that? That means when query comes, this query queue comes, I show the ad for A2. But that does not mean that the customer clicks on it. And unless the customer clicks on it, I don't get a revenue. I means the search engine here or the the service provider, right? So I don't get the revenue. So essentially, every time we are talking about a bid, it actually means bid times the click-through rate. Okay, so which can be, of course, obtained from the historical data and so on. Because
So
every time it, yes.
can we make the ad unclickable? I mean, so unclickable, so unskippable. For example, YouTube does that, right? Because it gives unskippable ads before the starting of each video. So for every advertiser, do they get the same revenue by the ads since every viewer has to see the ads?
Right. So basically, so there are options, right? In YouTube, there are options. If I mean, I have never done that, but if you ever monetize some of one channel and make YouTube channel and monetize that, you can make different options. So that I think those are given to the advertisers. So one option is, okay, so we are actually going into stories now, which is fine. So, so based on that, obviously the pricing will change. But as soon as some advertisers makes an okay, not advertiser. So in YouTube, what happens? The channel owner wants to make money, and YouTube is the meta owner, right? So YouTube is kind of the higher level one which takes the commission from everything. So if you are creating content on YouTube, this is going one level higher than Google search. Then I have some videos and I have monetized my channel. The ads that will be shown there, the ad will be shown, but then again there is a question of, so every ad may have other options, right? So there can be, in some ads there may be banner pop-up ads here and there which are clickable or not clickable, and some ads are just like TV ads. You have to see it, and then whether you act on it or not does not depend on this particular video. You have to do it elsewhere. It's like when I see something on TV, I cannot immediately click on it, right? Click on it and buy. I have to go to the shop and buy something, something like that. So I think YouTube has different options. If you make your, if you give an option of showing ads which will run through all 20 seconds or 30 seconds, and then your video will come, your viewers may get disturbed. They may not like it. On the other hand, if you give a skip option, your channel's content gets higher priority, where the ad gets a lower priority. So I'm pretty sure that the revenue will be slightly lower. So ad revenue will be slightly lower. So I think people, you know, I haven't really looked into that kind of things much, but I believe there are standard rules and thumb rules which people look into while deciding what kind of option they should choose. And then whatever ad revenue comes, YouTube makes part of the money, and the channel, the person creator or whatever, they make part of the money, right? So that's basically it. Okay, so basically my point is this portion, this bid, in we were talking about search ads. There it means bid times click-through rate. In YouTube or in other kind of cases, it will correspond to some other appropriate function of the bid. Okay, so that may be, that function will be different for ads which are which has to run through and then your video will start, or ads which can be skipped after 5 seconds and then your video will start, right? So the function has to be different for both, because the advertiser ad may or may not be shown fully, so the amount of money that will be paid will also be different. It may also be how much of my ad has been seen, right? So the viewer may skip the ad or may not skip the ad. If the viewer did not skip, maybe you get more money. If the viewer skipped it, maybe you get less money or whatever. I don't really know the details, but one can actually look at the documentation or YouTube terms and conditions. All right, so now let's basically what I wanted to point out is this bid we are talking about is bid loosely, but technically it is actually bid times something. So some other function of bid. So generalized balance will work in the following way, that suppose advertiser AI has bid $xi or amount xi for query Q. So we need to define, when a query comes, whom should I allocate it to? So suppose AI has bid xi. Now, of course, it may be 0, which means AI has not bid on query Q. And suppose we have many advertisers. And then fraction of AI's budget currently remaining is Fi. Okay, so Fi is a number between 0 and 1. Then let's define psi I to be xi, the bid, times 1 minus e power minus Fi, or 1 minus 1 by e power Fi. Then the algorithm would work in the following way. It's pretty similar to the previous one, but just a bit adjusted or adapted. Allocate query Q to the advertiser for whom this psi I is maximum. Of course, if there is a tie, you break it arbitrarily. So this means if the bid is higher, this goes up a bit. Also, if the unspent fraction of unspent budget is higher, then 1 by e power Fi, right? So if Fi is higher than this 1 by e power Fi is lower, that means 1 minus this is higher. So basically, you are for higher unspent budget fraction or higher bid, both will actually get a this thing. Obviously, it's not just any formula. This people have proved with this that this algorithm again achieves competitive ratio the same as 1 minus 1 by E. This is the result. This is, I think, 2005 Fox paper by this Mehta, Saberi, Mehta, Vazirani. So basically, often the balance algorithm is credited to them, but the balance algorithm for this particular application with all these constraints is actually credited to them. Otherwise, the algorithm that we first started with, the simplified for version and all, that's actually a pretty well-known online graph algorithm called B matching. So that's not that is actually not this paper. All right. So yeah. So these are the two papers I was talking about. And let me remind you, you should actually read up this portion. And yeah, this is the main reference. Okay. So any question immediately? All right. So let me stop the recording and then we'll discuss on the next class or other schedule.